All right, so we didn't get to the last section of chapter 7 or was it chapter 7? And there were quite a few questions through perusal about that. So I wanted to make sure that you had a little bit more explanation of the relationship between force and potential energy, and also looking at the diagrams. So we're going to start with the definition of work, which is the dot product of force and displacement. And we found that this was equal to minus the change in potential energy. Now, to simplify things, we're going to assume that the force is in the x direction, and therefore our displacement we'll look at is in the x direction. And so this expression is going to change to f of x dx equals minus delta u, and that's work. But if we want to take away the integral sign, that means that we're not looking at an entire big displacement in x, but we're looking at just the little increment of displacement. And so instead of work, then we're looking at a little piece of work, and then this is equal to fx dx, and then we call this minus du. And so hopefully you can kind of see how we get this from here. Now, when we do that, we can actually rearrange this expression and find that there is this relationship between the potential energy function and the force. So what we're doing is doing what we did previously, where we used the definition of work done by a particular force to find its potential energy function. Now we're going backwards. And what this expression tells us is that if we know the potential energy function, we can actually figure out what the force is that's associated with it. And so we have this relationship that the force is minus the derivative of the potential energy function with respect to x. Keep in mind, what would this look like? What is this on a graph? And du dx on a graph of u versus x would just be the slope. So that's something that we want to keep in mind, that if we have a graph of the potential energy function, the force is actually related to the slope. It's actually minus the slope, and we're going to see that in a few slides. So we have that relationship in one dimension between the force and the potential energy function. Remember our statement in the previous slide that said that du dx in terms of a graph of potential energy would be like the slope of the potential energy. And so we can make the other conclusion that if there's a large slope, then that's going to correspond to a large magnitude of force. The sign is going to really be the direction of the force. And the other thing we can get from that, and this is something that we want to sort of continue to think about as we go through learning more and more physics, and what I'm saying is as you go to higher levels, is that another thing that we can take away from this expression is when we have a conservative force, and remember that this force right here has to be conservative because it's related to a potential energy function, and only conservative forces do that. And what we see there is the conservative force will try to push the system to a lower potential energy. And that's sort of a natural state of physics that we think about, that potential forces or things tend to want to go towards lower potential energy. The example that I give is, a ball will roll down a hill. Gravity will tend to take the ball from the top of the hill to the bottom, and we know that at the bottom of the hill it has a lower potential energy. Here's a graph of the potential energy function of a spring, and so let's look at this a little bit, this relationship. So if we choose a point right here, and we look at the slope of this line, of this tangent line, that would be equal to du dx. And this slope is actually positive, right? So that means that this force in this situation is negative because of that negative sign right there. And so over here, the force is going to push the object to the left. Now we do the same thing over here. The slope of the tangent is du dx. This time it's negative, which means the force is positive. And so over here, we see that the force is to the right. Right here, the force is 0 because the slope is 0. So this is really sort of allowing us another way to understand how a spring works. We already know that the restoring force is equal to minus kx. You can actually get that expression by taking the derivative of 1/2 kx squared. But we also talked about how in a spring, the force of the spring tends to pull it towards the equilibrium position. And you can see from the direction of these two forces that that's exactly what they're doing. They're always trying to pull the object to x equals 0. The place where the force is equal to 0 is called the equilibrium. The equilibrium point. And we have different types of equilibrium points. We have stable, we have unstable, and we have neutral. And let's talk about how we determine what kind of equilibrium we have. So when the potential energy function has a minimum where it has an equilibrium, then that's called a stable equilibrium. Let's go back again and think about the spring. This was 1/2 kx squared, which was equal to the potential energy of the spring. Remember that the force on this side was to the left, and to the right on the left-hand side, and here's your equilibrium point. This is also a minimum of the potential energy function, and so by definition it's a stable equilibrium. Another way to think about whether an equilibrium is stable or unstable is to think about a small displacement from the equilibrium position, either to the left or to the right. And think about if I pulled an object a little bit in either direction, what would be the direction that the force would push it in? And we see that with either of these displacements, the force of the spring would push the object back towards its equilibrium position, and so it would tend to go back to it if it was displaced a little. That makes it a stable equilibrium location. Similarly, or in contrast, if we had something more like this for our potential energy function, and this would be my equilibrium point, right here where the slope is 0, we could see here on the right-hand side, the slope of this graph is going to be negative, which means the force would be positive, and so it would be to the right. And on the left-hand side, our slope is positive, which means our force would be negative or to the left. Now, when we think about displacing our object just a little bit from the equilibrium position, we see that the force would actually keep pulling it away on either direction. And that's why this is unstable. That's the situation where the, if you do a displacement from the equilibrium, the object just goes away from it and can't come back. An example of this is sort of like a physical pendulum, like a rod that's pivoting around a location. If the rod is at the bottom, this is a stable equilibrium, because if we swing it back and forth, it'll just kind of tend to oscillate about that location. But if we have it vertically upside down, it could potentially be balanced there in an equilibrium position, But if we just tap it ever so slightly, it's going to swing down and not come back to that equilibrium point. And so that makes it unstable. So here are some pictures of situations where we have different types of equilibrium. If we have it flat, of course, it really isn't either. It's just, we call that neutral. But here we see stable. Notice sometimes I like to think of the visual. It's like putting a ball in a bowl, and it will oscillate around this equilibrium position, where the unstable is like an upside down bowl. And if you push it at all, it's just going to fall right off the top. Here's a question. It says, here's the potential energy function for a particular situation, and it wants to know at the 3 points labeled, what is the magnitude, where is the magnitude of the force on the particle the greatest? And so what would we look for? The magnitude of the force is related to the slope of this graph, and so we would ask, where is the slope the greatest? We could eliminate point y because the slope there is roughly 0. And also, as I look at z, the slope of that graph is very small at that location, and so then the slope would be greatest at point x, and so that would be my choice for this particular question. Here is then making another relationship between potential energy and kinetic energy. Keep in mind that the total energy is potential plus kinetic. And so sometimes when I'm drawing a graph, what I can also imagine is that the system has a total amount of energy that goes across vertically, and that's represented by that horizontal line. And then we can say that sort of from here to here represents the potential energy, and then that means that the remainder of this is the kinetic energy. And so when I know that, if I look at the particle at point D, it moves in the negative x direction. It's saying, when does the particle have the greatest speed? So we want to see where the biggest space is between the potential energy function and the energy, and that would be at point B. This is where this kinetic energy is largest. Notice the potential energy is actually negative here, and that's allowable. And so at point B is where it would have the greatest speed. Now finally, we looked at really simple situations where the force was just in one direction, but it's possible to have a force that depends on more than one variable. It can depend on x, y, and z. And so these relationships change from total derivatives to partial derivatives. And that's what that little symbol looks like. Now, partial derivatives may seem very unfamiliar to you, and it's probably likely that you've never seen something like that before. But it's not really that hard to imagine. What you're looking at is the situation where the force might be like 3xy minus 2z. That depends on all the different coordinates. And so when we want to look at how that force changes with one particular variable, we're taking the partial derivative. And when we do that, we treat the other variables like they're constants. And so let's look at an example. So I'm going to make up a force again. It is equal to 2xy minus 3zy plus 2x squared. And so that's my force in 2 or 3 dimensions. That's my u. And so the force in the x direction is minus the derivative of the partial derivative of u with respect to x. And so when I'm taking the derivative, I'm going to treat the y and the z just like they're constants, just like they're numbers. And so for the first term, I get 2y. And for the second term, I get 0 because all those are constants when I'm taking the partial with respect to x. And then for the last one, I get plus 4x. Now I'm going to do and find the y coordinate, and that's minus the partial of u with respect to y. I put the negative sign out there, and so I get, for the first term, 2x, for the second term, minus 3z, and for the last term, it's just 0. And finally, for z, it's minus the partial of u with respect to z, and I get 0 minus 3y plus 0. So this force, the way I would write this, is it would look like minus 2y minus 4x is the x component, and then 3z minus 2x is the y component, and then minus 3y is the z component. So we don't really have to do that really just for maybe a example problem or a homework problem, but that's how you would do that. And that is it. I hope that this is helpful.